In real life, motion is hardly ever in a straight line, that is, in only a single dimension. A real object would move in all dimensions and would have trajectory that can't even be fit into a mathematical equation. We have touched upon elements of multi-dimensional motion earlier when we talked about position vectors and displacements, where even though the net displacement was technically a straight line, the motion itself had components in all three dimensions, and we simply calculated displacement by finding the difference between the final position and initial position measured in terms of the position vectors. Working with multiple dimensions becomes easy if we start treating quantities as scalars and vectors. And when vectors are broken down into components along dimensions, we can simply make our calculations for each dimension independently of the other two. Here's how. If a particle moves through a displacement delta r in a time interval delta t, then its average velocity v average is given by delta r by delta t. This tells us that the direction of v average must be the same as that of delta r. We know that any vector can be written in terms of its components, which can be tagged along with the respective unit vectors. So if we do that with the vector delta r here, we can write this equation as v average equal to delta x by delta t I hat plus delta y by delta t j hat plus delta z by delta t k hat, which means that the average velocity has components delta x by delta t along x-axis, delta y by delta t along y-axis, and delta z by delta t along z-axis. We can follow the same concept and write a similar equation for instantaneous velocity. And the components of instantaneous velocity along x-axis, y-axis, and z-axis would be Vx equal to dx by dt, Vy equal to dy by dt, and Vz equal to dz by dt. And we can extend the same rule to acceleration to find its components along x, y, and z axis as ax equal to dvx by dt, ay equal to dvy by dt, and az equal to dvz by dt. We next consider a special case of two-dimensional motion. A particle moves in a vertical plane with some initial velocity v0, but its acceleration is always the free fall acceleration g, which is downward. Such a particle is called a projectile, meaning that it is projected or launched, and its motion is called projectile motion. Many sports involve the study of the projectile motion of a ball. For example, when a batsman hits the ball for a six, the motion of the ball is an example of projectile motion. Please note that a projectile might be a cricket ball or tennis ball in flight, but it is not a bird in flight. That is because the bird flies in the air by working through the air with its wings and body, and is not in the influence of the free fall acceleration alone. In analyzing projectile motion here, we'll make one basic assumption, that air has no effect on the motion of the object, which implies that the motion is purely under the influence of the force of gravity acting downwards on the object, and no other force acts on it while the object is in flight. Given that assumption, we shall analyze the path followed by the projectile. Suppose we align our coordinate axis such that the motion of the projectile is totally in the xy plane. Let the vertical direction be aligned with the y-axis and the horizontal be the x-axis. Also, let's place the origin at the point from which the projectile is launched. And let's further assume that the projectile is launched at an angle theta 0 with the horizontal x-axis. The projectile is launched with an initial velocity v0 that can be written as v0 equal to v0x I hat plus v0y j hat. The initial velocity vector v0 has to align with the angle at which the projectile is launched, since that would be the direction of the initial velocity as the projectile shot into air, that is, at an angle theta 0 with the horizontal x-axis. The component of v0 along x-axis would be v0 cos theta 0, and the component along y-axis would be v0y equal to v0 sin theta 0. During its two-dimensional motion, the projectile's position vector r and velocity vector v change continuously, but its acceleration vector a is constant and is always directed vertically downwards. The projectile has no horizontal acceleration. In projectile motion, the horizontal and vertical motion are independent of each other. That is, neither motion affects the other. This feature allows us to break up a problem involving two-dimensional motion into two separate and easier one-dimensional problems. one for horizontal motion with zero acceleration and one for vertical motion with constant downward acceleration. In the horizontal direction, since there is no acceleration, the horizontal component of the velocity v0x remains unchanged throughout the motion. At any time t, the projectile's horizontal displacement x minus x0 from an initial position x0 is given by x minus x0 equal to v0xt. And since v0x is equal to v0 cos theta 0, we can write x minus x0 as v0 cos theta 0 multiplied by t. The vertical motion is the motion of an object in free fall. The acceleration is downward and hence equal to minus g. We can write the equation of motion for vertical displacement as y minus y0 equal to v0 sin theta 0 into t minus half gt square. We can further write the other equations of motion in the vertical direction, that is equations involving the vertical component of velocity at any time t. Let's call it vy. So vy equal to v0 sin theta 0 minus gt and vy square equal to v0 sin theta 0 square minus twice g multiplied by y minus y0, which is the displacement in the vertical direction. The vertical component of velocity behaves just as for a ball thrown vertically upward. It is directed upward initially and its magnitude steadily decreases to 0, which marks the maximum height of the path. The vertical component of velocity then reverses direction and its magnitude becomes larger with time. We can find the equation of the projectile's path, that is its trajectory, by eliminating time t between these equations. And this is what we get. Y equal to tan theta 0 multiplied by x minus gx square divided by twice of v0 cos theta 0 whole square. In deriving this, we have assumed x0 as 0 and y0 also as 0. Because g, theta 0 and v0 are constants, this equation is of the form y equal to ax plus bx square, in which a and b are constants. This is the equation of a parabola. So the path of a projectile is parabolic. The horizontal range r of the projectile is the horizontal distance the projectile has traveled when it returns to its initial height, that is, the height at which it is launched. That means the net change in height during the journey would be 0. Let's start with the basics, that is, evaluate this motion in the horizontal and vertical directions separately for the entire journey of the projectile while it covers its range r. In the horizontal direction, x minus x0, that is r, would be equal to v0 cos theta 0 multiplied by t. And in the vertical direction, y minus y0, which is 0, would be equal to v0 sin theta 0 t minus half gt square. Eliminating t between these two equations, we can derive that the range r is equal to v0 square sin twice theta 0 divided by g. Note that r has its maximum value when sin 2 theta 0 is equal to 1, which corresponds to 2 theta 0 equal to 90 degree or theta 0 equal to 45 degree. Therefore, the horizontal range r is maximum for a launch angle of 45 degree. Please note again that we have assumed that the air through which the projectile moves has no effect on its motion. However, in many situations, the disagreement between our calculations and the actual motion of the projectile can be large because the air does resist the motion in real life. तो भाइयों इतना ही है in terms of concepts for two-dimensional motion and projectiles. जो असली challenge है वो उनको apply करने में है to intricate situations and for solving problems. So why don't you start trying and let me know how it goes. Reach out to me in the comment section or email me, or you can write to me on my Facebook page. I'd love to get in touch and help you proceed. Remember that the key to being good at physics is knowing the basic concepts very well and not memorizing formulas. Keep that in mind and I'm sure you'll do great. Thank you and enjoy learning physics. Bye-bye.